Hello! In this module we will learn the sequential function chart, also called the SFC language. I will first present the SFC language, how it works, how it is written, and then we will make an example. An SFC chart is a set of steps and transitions. Each step represents a well-defined state of the process. Each step may be active or inactive, and transitions represent the events that move the activity from a step to another. In this example, we have a box that arrives on a conveyor. The sensor 1 is then true, so the first transition can be crossed. The motor of the conveyor is then started until the sensor 2 becomes true, and then the motor is stopped and the robot takes the box away from the conveyor until it is no longer on it, so sensor 2 is false. How do we represent steps? A step is represented by a square box. Each step is identified by a unique number. A step can be named in program instruction using GSNNN with NNN, the number of the step. A step is a local object. A program cannot have access to a step defined in another program. A step is either active or inactive. The step activity can be used in the program expressions using GSN.X, which is a Boolean expression. A step represents a stable state of the process. The duration of a step activity can be used in expression using GSN.T, which is a time expression. The transitions. The transitions are represented with a horizontal line that crosses a vertical line drawn from a step to another. The default direction for vertical links is from the top to the bottom. Each transition of an SFC program is identified by a unique number. A condition is associated to each transition. The condition is a Boolean expression. If no condition is entered, it is assumed as always true. Here are examples of different conditions for the transitions. A transition is crossed when all steps linked before the transition are active and the condition of the transition is true. When a transition is crossed, all steps linked before the transition are deactivated and all steps linked after the transition are activated. When the same step is linked before and after the transition, it remains active. There is no pulse in its activity signal. So how does an SFC work? The chart must have an initial situation that shows the state of the process when the application starts. The initial situation is represented by initial steps drawn with double line border. There can be more than one initial step in this chart. The transitions and their conditions describe how the SFC situation changes, and each active step is marked in red. The execution of an SFC is sampled according to the target cycles. The following steps are done at each cycle for each step. Evaluation of the chart. All valid transitions are evaluated. We speak here of the transitions following active steps. And then execution of the chart. All active steps are executed in the order of the graph, from left to right and up to bottom. If several consecutive transitions are true in a branch, only one is crossed at each cycle. Several transitions may be linked after the same step. The divergence represents several possible changes of the SFC situation according to the condition of each transition linked after the step. The conditions of a divergence are evaluated with the default priority from the left to the right. Several steps can be linked after the same transition. Branches linked after the transition represent parallel processes. All parallel branches must finish with a link to the same transition, which is a convergence. Parallel divergence and convergence are represented by double horizontal lines. In order to avoid blocking situations, there should be no link between branches and outside the divergence. It is possible to jump to a step. The jump symbol may be used to represent a link from a transition to a step. This replaces the actual drawing of the link and simplifies the chart. The destination step is expressed using its identifier, its number. A jump to a transition is forbidden as it corresponds to a convergence of parallel branches, and we said that parallel branches must be explicitly drawn. So when must we use an SFC? SFC must be used when you need to manage sequences of stable process states. Using SFC avoids complex switches and the declaration of multiple flags in program. And more generally, when you think when the process is in that situation, then you should use the SFC. So now, when must we not use it? The SFC should never be used as a decision diagram or flowchart for describing an algorithm. This leads to complex SFC charts and bad performances at runtime. Never use a step to represent an intermediate point within a calculation. Prefer the ST language in that case. Generally, when you think if, then else, then do not use the SFC. How do we write a transition? Each SFC transition must have a condition that indicates if the transition can be crossed. The condition is a Boolean expression that can be programmed either in ST or LD language. In ST language, enter a Boolean expression. It can be a complex expression including function calls and parentheses. For example, bForce and parentheses balarm or minimum I level and 1 different from 1. In LD language, the condition is represented by a single rung. The coil at the end of the rung represents the transition and should have no symbol attached. For example, the rung below with the coil that have no symbol attached. Let's make a small exercise to practice the SFC. We will reproduce the following chart in Straton and will use the keyboard shortcuts described here. So I insert a new program. I call it practice SFC, and I select the SFC sequential function chart language. I open it. I see that I already have an initial step when I open the program. So to have the same diagram as here, I insert a divergence, either by clicking on the icon here or by using the key X that is represented here in between parentheses. So I can click on this icon. Then I add a transition, so either with this icon or with the key T. Then I enter a step with this icon or the S key. Then another transition, so T, another step, S, another transition, T, and then I have a convergence, so another divergence here, and a jump, either with a jump this icon here or the key J. And I enter the number of the step I have to jump to, so the first one. Then here I have to add another divergence, but this time this one, so I can use this icon or the D key. I enter another transition, T, S for step, T for transition, S for step, T for transition, and here I have a convergence, so I can use this icon or the C key. Okay. Then I add the conditions and of the transitions. I have to double click on the transition to open this window here, where I can enter the condition. So I enter the variable a that I have to declare. It is a boolean. Okay. I have here to wait for 1 second. So I use the duration of the step activity with GS number of the step 3.t greater than t, it take 1 second. So it is important to use greater than rather than equal, as it may be possible that Stratton considers that there never is the perfect equality. You may have 0.99999 second and then 1.0001 second, but never 1.000 second. So to avoid this problem, prefer to use greater than. And the last transition is not, so I have to double click on it, not A. And the transition of the other branches, I enter here B, that I have to declare. It is a boolean. Here I also have 1 second, so GS, okay, sorry, made some GS8.t greater than T, it take 1 second. And here I also have to enter a condition, a time of 1 second, so GS10.t greater than T dash 1 sharp 1 second. Okay. So here you can see in your program that Stratton has numbered the step and the transitions in the order we created them. So I can click on this icon here called Renumber, and then the step and the transitions will have independent numbers from one another. And I see here also that the second branch starts at 101. So now that we've seen the transition, let's focus on the actions in a step. Actions can be attached to a step. The execution of the actions depends on the action qualifier. P or P1, the action is executed once when the step becomes active, and the action is executed on each cycle while the step is active, and P0, the action is executed when the step becomes inactive. So it can be represented by these diagrams. Step 1 is first inactive. Then it becomes active, so at that same cycle, the action defined in P1, if there is any, is executed. Then while the step is active, the action defined in N is executed, and when the step becomes inactive, the action defined in P0 is executed. If at this time the step 2 is activated, then at this same cycle, the action defined in P1 for the step 2 is executed. So our example can be rewritten like this. When sensor 1 is true, action 2 is activated. So in P1 the motor started, and then when sensor 2 becomes true, the step 2 is deactivated and the motor stops. It is possible to use function blocks in SFC, but note that an SFC action is executed only when it is valid according to the step activity, and a function block remembers its last call. For example, a typical error is to use a counter block that counts the N action, that counts in the N action. the counter is not reset when re-entering the step, so the counter has the value, if the counter had the value x when leaving the step, it will still have the value x when re-entering the step. Another typical error is to use a trigger function, as the rising edge happens only once and you may be blocked in the step waiting for the rising edge to activate the transition. This is the same for the transition, with the use of P and N contacts in the transitions written in ladder, so avoid using them. The child program. Each SFC program may have one or more child program. A child program is written in SFC and is started or stopped in the actions of its father program. A child program may also have its own children. When a child program is stopped, its children are also implicitly stopped. But when a child program is started, it must explicitly in its action start its own children. The command name of the child parenthesis n starts a child program. In this case, the child SFC is started when the step is activated and killed when the step is deactivated. The command name of the child parenthesis s starts the child program when the step is activated. But when the step is deactivated, it is still running, so it corresponds to a set. And the command name of the child parenthesis r stops the child program when the step is activated, so it corresponds to a reset. Let's make an exercise to practice the use of father and children SFC. We'll program a traffic light system. There will be one father SFC that manages two modes, the night mode with yellow blinking and the day mode with the normal sequence green, yellow, red. Each mode is managed by a child SFC. We'll have 4 Boolean global variables, be green, be yellow, be red, and is it day. So in my Straton project, I insert a new program. I call it traffic light, and I select the SFC language. Okay. I declare the global variables is it day, be green, be yellow, and be red. So I will first deal with the father SFC that manages the two modes. So I open my program and I add a divergence to have the choice between day or night with a transition for each part and a step and another transition and finally a jump back to the first step. I can remember. Okay. So the branch on the left will deal with the day mode and the branch on the right with the night mode. I open so for this I have to add the transition. Is it the variable, is it day? If it is true, we will say that it is the day. So, and here not is it day? If it is the night, it is not EasyDay, remember I can click on Control Space to enter the name of the declared variable, and here is a day. Okay. I open the step of the day mode by double clicking on it. On the right, I have a window with 5 spaces that opened. If they do not all appear, I can click on the icons on the top right of the window to add or remove a section. The first section is the section where we manage the children SFC. The second one is the P1 section, so the action that is executed once when the step becomes active. The third one is the end section, so the action that is executed as long as the step is active. The fourth one is the P0 section, so the action that is executed only once when the step is deactivated. And the last one is a note section where you can write a description of what your step is doing. For example, I enter day and I see here into my step that day is written. So for this step, I want to start the day mode child SFC, and if the step is deactivated, I want this child SFC to stop. Therefore, I enter day underscore mode, parenthesis n, close parenthesis, and semicolon in the first section. Day mode will be the name of the child SFC. If it is not the day anymore, I have to switch to the night mode. So I set the transition, yes, as I said, the transition here is not EasyDay. The step of the second branch manages the night mode. As for the day mode, I start the child SFC night mode, parenthesis n, parenthesis, semicolon. And I add a description in the note section, night. Okay. So now I have to create and program the 2 children SFC. So I insert a new program. I call it day mode. I enter the same name as the one I used in the father SFC. I select the SFC language. And then I click on child SFC program. And I can select the father SFC among all the SFC programs of my project. So here it is, traffic light. Then I click on OK, and I see in the tree that the day mode SFC is right under the traffic light SFC. So in this day mode, the initial step will manage the red lamp. So I open it. I add a description, for example, red. To remember that this step manages the red lamp. Then I will use the P1 section to light on the lamp, so be red double point equal true, semicolon. And I use the P0 section to switch it off, so be red double point equal false, semicolon. Then I add a transition after this first step with T. And I want that the red light stays on for 3 seconds, for example. So for the transition, I enter GS1.T greater than T 3 seconds. Then I add another step with S that will manage the green light. As for the red light, I switch on the light when I enter into the step, and I switch it off when I leave the step. So I use the P1 and P0 section. P green double point equal true, semicolon for P1, and B green double point equal false, semicolon for P0, and here I can enter green. Let's leave this step active for 2 seconds, so I add a transition with T, and the condition is gs3.t greater than t 2 seconds. I add a last step for the yellow light with S, and I do the same as for the other lights. B yellow double point equal true semicolon in P1, and B yellow double point equal false semicolon in P0, and here in the node yellow. We leave this step active for 1 second. So I add a transition with T with the condition gs5.t greater than t 1 second. Okay, and finally I add a jump with J to the first step to close the loop. I can remember if I want to. So to remember, I have to close all window here. I remember, and I see here that in my transition, Straton has automatically adapted the number of the transition. So now I add the night mode. So I insert a new program. I call it night mode. Select the SFC language, click on child SFC program, and it is the child of the traffic light SFC. And I click on OK. I open the program. So the first step, this time we'll manage the yellow light. So I will manage it as for the lights of the day mode. In P1, I enter B yellow double point equal true semicolon, and in P0 B yellow double point equal false semicolon, and here I can enter yellow on in the node. I will let it on for 1 second, so I add a transition with the condition, so transition T with the condition gs1.t greater than t 1 second. Sorry. And then I add another step with S that does nothing to let the light off, and I let it off for 1 second also, so I add a transition with T, and the condition is gs3.t greater than t 1 second. And finally I add a jump to the first step to close the loop, and I can remember again. So now I build my project. I have no error. I can start the simulation. And I see here that my variable ExitDay is false, so the SFC traffic light starts its child night mode. We are here in the night mode, and we see that the B yellow variable is blinking. Let's go into traffic light SFC. We see that the step night step here is active. Now if I set the ExitDay variable to true, I should go into this branch of the SFC and then activate the day mode SFC. Okay, I see here that I have activated this step, so I have activated the day mode. I see here now that day mode is no longer written in red with no cross. And I see here my variables changing from false to true according to the sequence we programmed. So red, then 3 seconds, then green, 2 seconds, then yellow for 1 second, and back to red. So to conclude, in this module we learned how to create an SFC program, and we saw that we can have different levels of SST with the Children SFC. That's it for the SFC module. Thank you for watching this video.